Okay, so from the imaginary experiments of the double slit, we arrived at an object that is meant to describe the particle, which looks like this. Okay, so we want to find a constraint for this kind of object. We want to find an equation that implies this kind of solution, this kind of object for the description of the particle. So let me just point out that the energy, we showed that the particle has wave-like properties that appear here can be written in terms of particle-like properties, and in particular, the angular frequency can be written in terms of the energy, which is h bar times omega, where h bar is h over 2 pi, and I think in a previous video we incorrectly wrote the not the angular frequency, but the actual frequency 1 over the period as nu with I think we wrote h bar nu here, and so we made a mistake. We're off by a factor of 2 pi. That can happen, but the correct relationship is that E is equal to h bar times omega, and so we can replace this quantity as follows, minus, we have E over h bar times t in that equation. Of course, we can then replace the wave number with the momentum, and we'll eventually do that, but for the time being, we want to sort of motivate the origin of the equation that gets us this kind of object, and the crucial thing there is the energy. And so let's go back to thinking about how it is that energy constrains the solution to the dynamics of some kind of system. So if we go back to mechanics and we think of F equals ma, right, that's the equation that governs the motion of an object. There, of course, you solve for the acceleration given the force, and from that you can get the velocity and the position at all times. But that's a very difficult thing to do in general, and so we develop these techniques that involve the concept of energy by manipulating F equals ma, in other words, integrating both sides over some distance, and recognizing that I can write the acceleration in terms of the velocity, and then when I integrate that, I can turn this into, this is a number, right, because there's a dot product here and there are vectors there, so I get numbers. I get a difference between two numbers, the final kinetic energy minus the initial kinetic energy. Right? And we've seen that. And on the other side, if I can write the force in terms of the gradient of a potential function, then I end up with minus u final minus u initial, right, where f is equal to minus the gradient of this u function. Then this leaves me to a concept of energy conservation where u initial plus k initial is equal to a u final plus a k final, right? And that's the concept of energy conservation, where the energy u plus k is always the same. That's what this relationship is telling us. And so, for example, for gravity, right, in the simple problems where gravity is treated as a constant force of magnitude mg, we have that the total energy is 1/2 mv squared plus an mgy, kind of quantity, which we could also write as the momentum squared over 2m plus an mgy. But the key there is that the total energy provides a constraint that allows us to solve for things like the speed and the height of an object. So, for example, if we drop an object from some known height, we can figure out how fast it's going at different heights by applying energy conservation, right? So if we drop an object, the form of this has only the mgy term, right? Say the height is known, it's h, then this becomes mgh, and it's dropped, so this is 0, and then we set this equal to the energy at the bottom, when the object hits the floor, for example. If we want to know the speed with which it hits the floor, then we have a 1/2 mv squared term there and no mgy, because the y would be 0 for the floor. So using energy conservation, as opposed to going through F equals ma, which would force kinematic equations, we can get our answers to the dynamics of an object that obeys that energy conservation equation. The same thing applies for our particle in the double slit experiment, right? So psi depends on energy, right? So energy constrains this psi. We just put in energy into the psi equation, into the wave equation. So the total energy, in some sense, informs psi. Well, how does it do that? Well, let's again write down that psi is equal to a e to the I times kr minus e over h bar t. And so we can figure out how to get the energy out of this object. And notice that you need a time derivative. If I take the time derivative of this function, psi, I will get the function back, but I will get also this minus I times this time, this term in front of the time part, times psi itself. And so I can sort of turn this around and say that if I bring all of this to the other side and get rid of the minus sign by multiplying by I over I, right, and I squared is -1, then I can say I h bar d psi by dt is equal to E times psi. And so that looks like an equation that has something to do with the energy of the system. And the equation is basically saying that the rate at which the wave function varies in time is related to the energy that is inherent in this psi function itself. So this is our first attempt at trying to produce an equation for psi, an equation that psi obeys, as determined by the fact that psi has some energy associated with it.